Yeah, Kamsan, everyone. Let's start off. So last class we have done with KTG. Others do keep your cams on. Great. So we'll be starting off with thermodynamics. Chapter as such, right? It is not tough, but there are some standard results and formulas. As long as you know your standard results, most of the chapter is doable actually. It's not really that out of the world. So let's go ahead. The starting is zeroth law of thermodynamics. So why do we even call this zeroth law of thermodynamics? The thing is, people figured out the first law, second law, and then they realized there is something even more fundamental they forgot. Now you can't change the laws right from one end to books are already printed, expensive. So they said let's make it a zeroth law. Means tomorrow if they find something even more fundamental, they'll call it minus one law. So what is this exactly? And why do you think it is so obvious? I think after the statement you'll understand. If two isolated systems A and B are in thermal equilibrium, and if systems B and C are in thermal equilibrium, so when you say thermal equilibrium, meaning if you touch these two bodies, there will be no temperature change. So literally they are in same temperature. If systems B and C are in thermal equilibrium, so thermal equilibrium. So when they're brought into contact, there'll be no heat exchange. Then A and C are in thermal equilibrium. So kind of it looks like, you know what? If A and B have same temperature and B and C have same temperature, then A and C will have same temperature. Now it kind of looks like obvious actually. That's the problem. People didn't think it's a law. But then you need to understand one thing. When you say something is obvious, the problem with the word obvious, you know what? It means it is valid for any property. Let me give you some crude example. If A and B are friends, and if B and C are friends, there is no guarantee A and C are friends. To give something even more technical, think of like this. Let's say if A is going with speed V, and let's say B is at rest, and let's say C is also going with V. A thinks B is moving, relative velocity. C thinks B is going, relative velocity, but A thinks C is at rest. Did you see? If A thinks B is moving and C thinks B is moving, there is no guarantee A will think C is moving. A will think C is at rest here. So when you say something is obvious, it should be valid for everything. So this is not obvious. It is that for temperature, so it works, right? So you have to define it separately for each property. So for temperature, it is valid. So that's why we have to define the law. So as such, there are no questions or anything on this. It is just a definition there, right? That is a zeroth law. Next thing, the first law. So the first law of thermodynamics, it is, we'll just wrote on the statement there, dq is equal to du plus dw. So dq is the heat supplied, Now you have to be careful. Unlike chemistry, right? The convention is slightly different here. Du is change in internal energy. dW is the work done. So this is another form of law of conservation of energy. Meaning, think about it in simple terms. Whatever energy dq that I give you, either you save it or you use it. If I give you some money, either you can use it or you can save it, right? There's nothing else you can do. Think about it. Even if you throw the money, it is as good as like you're somehow using it, you're throwing it away. So same way, whatever heat that you supply to a system, either it will store it as an internal energy or it is going to use that to do some work. Clear with this? Now the difference between this and chemistry thing is the sign convention. In chemistry, if heat is released by the system, what do we call it? Exothermic process, we take it as positive. If heat is absorbed by the system, it's an endothermic process, we take that to be negative. So you need to understand in chemistry, we are more concerned about whether the system is exothermic or endothermic. But in physics, it is different. So if you look at the sign convention, so what we study is something else. So whenever in physics you think about thermodynamics, think about heat engines. So we are supposed to provide heat to an engine, maybe a steam engine or anything, and in return the engine is supposed to give you work. You're getting the concern here? Now you tell me, should the heat engine take heat or give heat? If you're having a steam engine or something, does it take heat or give heat? It is supposed to take heat. An engine is supposed to take heat and give you work. So our convention looks like this. Heat given to the system is positive because you want the engine to take heat. But in chemistry, it is reverse. If heat is given to the system, it becomes an endothermic. So be careful with that. You might get confused with the signs there. Heat rejected by the system. So the heat is given by the system. I don't want the engine to give me heat. I want the engine to take heat. That would be negative. Similarly, I expect the engine to do work. So work done by the system is positive. If you have to do work done on the system, you want to sit on the scooty and go, or you want to push the scooty and go. You don't want to push the scooty and go, right? So if you're pushing the scooty, you're giving work to the scooty. That is negative. So be careful with that convention. Clear with this? So that is one important thing about the sign convention. Be careful with that. So it matters, for example, see, if I had to give you some analogy, think of like this. Let's say if you're a coconut farmer, right? You're growing a lot of coconuts and you're selling it. What is more important? When you're selling a coconut, what are you exactly selling? Getting, let's say if you're producing 10,000 coconuts every year, what are you exactly selling? Are you selling the coconut water? It depends on your user. If you're selling it to people or tourists or people who drink the water, you're selling the coconut water. But if you're selling to a factory which is making jute car ropes or coconut fiber car ropes, you're selling the shell, isn't it? So the factory would take the coconut, will use the shell and throw the water actually. But the people who drink the water, they drink the water and throw the shell. You're getting it? So what is useful depends on your observer. Same way in chemistry, what was more useful? Heat was more useful, exothermic or endothermic. So we take that to be positive or negative. Whereas in physics, what is more we are useful is work done for us. So we are more interested in that. Getting it? So be careful with that convention. The first law also has a drawback. The first law, if you see, it simply says energy is conserved. That means as long as energy is conserved, the direction of reaction shouldn't matter. So basically, it does not tell us in which direction the reaction proceeds. Meaning, let's take an example. If you take your sodium hydroxide and if you put HCl, we are going to get some salt, we are going to get some water, and we're also going to get some heat. This is possible. Now, what first law says is, if I take salt, if I take water, and if I give heat, technically the thing is same. So I should get by hydrogen, sodium hydroxide, and the hydrochloric acid. This is not possible. So only first law can't tell you whether the reaction can proceed or not. So who tells you that is your second law. So the reaction or the process proceeds in the direction of increasing entropy. That you must have studied in chemistry. Gibbs free energy and stuff. If they have taught you, if you're not studied, that is okay. So the reaction proceeds in the direction of entropy. So you go from A to B or B to A, energy is conserved. But only one thing will happen, the other one won't happen. So who decides that is entropy. So even we do have entropy, but it is not as detailed as in chemistry. We're just doing basics of it. In physics, we don't talk much about entropy. Whereas in chemistry, you have that Gibbs free energy, that there's a lot of stuff is there. That's same thing, right? That's what I'm saying. Increasing entropy. So when you go from sodium hydroxide to acid, in that case, the entropy increases, but in the reverse, the entropy decreases. Clear with this, everyone? So there. So in the first law, if you see, we have three terms there: dq, du, and dw. Now let's see each term. How to get this? The first term, heat. This we studied in calorimetry. So dq is equal to ms dt. This we used for liquids or solids. Or dq is equal to nc dt. So the molar heat capacity is defined as C, which is 1 by N dq by dt. This is your molar heat capacity, which we did in calorimetry. So basically it tells you the amount of heat required per unit temperature per mole, right? This was done in calorimetry. Now, if you try to go from one state to another state, P to V, so let's say you can go in state one, process one, you can go in process two, you can go in process three. Depending on the process, the heats will be different. So delta Q1, delta Q2, and delta Q3 are not equal. So this depends on the path. It's a path-dependent process. So if you say I'm going from one A to B, you need to tell me how you're going, or else I can't find the heat produced, heat absorbed, or heat emitted, or whatever. So heat depends on the path. Next thing. So that is your first term there, dq. So this is what we are going to do. So for every process, we are going to figure out what is dq, what is du, and what is dw. That is the whole essence of the chapter actually. So in each process, we like to see how the heat or internal energy or the work done changes. The second term is your internal energy, which is U. So what is internal energy? Internal energy is nothing but kinetic energy of the gas molecules plus potential energy of the gas molecules. But we know for an ideal gas, the potential energy is zero. So in ideal gas, the molecules do not interact. So the potential energy will be equal to kinetic energy, which is F by 2 nRT. We derived this in the last chapter, KTG. Mein. So if you see everything we did before, they're popping up one after another. So the change in internal energy du is given by F by 2 nR dt. And again, if you look at this is a state function. It doesn't depend on F is constant, N is constant, dt is same for two states. That means if you go from A to B, you go any way you want. Process 1, process 2, process 3. Delta UAB is same. The delta UAB will be F by 2 NR TB minus TA. Independent of the process, it does not depend on the path. So if you say I'm going from A to B, you need not ask how you are going. Delta U will be same. This is a state function or it depends only on initial and final state. Can you tell me some other quantity which you know which depends only on initial and final state? Till now, whatever we studied in physics, can you tell some quantity which depends only on the state function? Which depends only on initial and final state? Pressure, gravitational potential energy. If you take a block from here to this height, does it matter how you go from here to here? What is change in potential energy? MGH, isn't it? Gravitational potential energy is a state function. It doesn't depend on path. Spring potential energy is a state function. It doesn't depend on how you elongate the spring. All potential energies are state functions. Getting this thing? So they don't depend on the path. They just depend on how your, what is the initial, what is the final state. F is your degrees of freedom. There, have a look at this page. So heat and du. Clear, everyone? That is the second term. So the third term, work. Out of all three, this is a little messed up one. So listen carefully. So we studied heat in calorimetry. We studied internal energy in KTG. So we studied work in work per energy. W. So work W would be what? Work is integral f dx. Right? And we know what is force. Pressure is force into force by area. Pressure is force by area. So if I substitute here, this will become force is pressure into area into dx. So area into dx. So area into length will be volume. So area into change in length will be change in volume, which is dV. So work done becomes integral PdV. There. Straightforward. Someone asks you what is work done, integral PdV. And if you remember, this also depends on the path. This is also a path dependent function. So if you take a PV graph, now see, when you take pressure and volume, both are positive, isn't it? Pressure can be negative, volume can be negative. That means a PV graph will be always in the first quadrant. So the area under the PV graph gives you work done. But how do we decide the sign convention? Now listen carefully. The first case, if the arrow is pointing towards right, what is happening here? When you go from left to right, that is point A to point B, volume is increasing. If volume is increasing, then dV is greater than 0. Therefore, work done from A to B is positive. So the area under the graph will give you the magnitude, whereas the direction is given by that sign. That arrow ka direction will tell you whether the work done is positive or negative. If the arrow is going from left to right, then the volume is increasing, work done is positive. Suppose if the arrow is going from right to left, now when you go from B to A, the volume decreases. So if you remember in work per energy, area above the x-axis was positive, area below the x-axis was negative. But here, there is no above and below. All the graph is in the first quadrant. So you have to decide whether the work done is positive or negative based on that arrow direction. So if the arrow is going from left to right, volume increases, work done is positive. If the arrow comes from right to left, then the work done is negative because volume decreases. Clear, everyone? This is positive work. This is negative work. Yeah. Next thing. Any doubts on this page? You can put on the main points. You'll be getting the PDF, anyway. So don't worry about writing down everything. The work done is integral PDV. That's the main thing there. Any doubts so far? Anything you're not clear, please ask. You got some queries, you can always unmute and ask, or else type in the chat box if you're feeling shy. But get it cleared, everyone. These are not difficult, but you should know your concepts, make it clear. Next one. Cyclic process. What's a cyclic process? If a gas undergoes, so you tell me, Vihan, volume is constant, pressure changes, what will you do? Seriously, that's your doubt. Then what is dV got? Zero. Work done zero. What is the problem? So if gas undergoes, the volume is increasing positive, volume is decreasing negative. If volume doesn't change, it is zero. dV is zero. So if a gas undergoes different processes, so let's say went from A to B, B to C, C to D, and eventually it comes back to the initial state. Such a process is called a cyclic process, meaning it's a cyclical, it keeps on repeating. So how do you find work done in this? For example, if you take a PV graph, this is a cyclic process. So let's say this is A, B. So the process is going like this. It's a cyclic process. Now see how to find the work done for this. Let's split this into two parts. I can split this into the upper semicircle where you're going from A to B, plus then I can split this into other lower semicircle. You are coming from B to A, the arrow is this way. Now just now we said what is work done under the graph? The work done is the area under the graph. So isn't this work? You should take the entire area below that semicircle, right? Is this positive or negative? Look at the arrow. Arrow is going from right to left, left to right. So in this process, the work done from A to B is positive. What about B to A? B to A, the area under the graph is this area, isn't it? And work done from B to A is negative. Is that making sense? And if I take this magnitude to be W1 and this magnitude is W2, so basically the work done is minus W2. Then the work done will be the area enclosed by the curve. Does that make sense? If you take this total red area and subtract this green area, what are you left with? The area enclosed by the curve. So in a cyclic process, the work done is the area enclosed by the curve. So in this scenario, it is W1 minus W2. There, have a look at this. Is that making sense, everyone? Why it is the area enclosed by the curve? So when you go from A to B, you're having a positive work, right? And when you're going from B to A, you're going a negative work. If you see, the positive work is more than the negative work. So the total work done will be W1 minus W2, which would be the area enclosed by that circle. So work done, there are two types. Huh? If you just have an open graph like this, A to B, one line or one curve, it is area under the graph. But if it is a cyclic process, you come back to the initial state, then it is area enclosed by the curve. This is what I said. Out of the three things, right? Internal energy is the easiest. dq is fine, heat is fine. Work done, there are variations. The sign convention makes it messy. Clear? Now, in this also we have a sign convention. So let's say we have a process like this. So if you have arrows like this clockwise, is this positive or negative work done? Work done is area enclosed by the curve. Magnitude, I know. What about the direction? Is it positive or negative? So that's what I'm saying. In PV graphs, right, the arrows will tell you the work done is positive or negative. There is no area above and below. If the arrows are in reverse. How do you decide something is positive or negative? See, here, when you're going from A to B, from A to B, volume is increasing. Remember, the formula is integral PdV. So volume is increasing at high pressure. So when you go from A to B, the pressure is high. Means you'll do more positive work. But when you come from B to A, when you come back in the reverse, the volume change is same, You come back to the same volume, but you're coming at a lower pressure. So in the formula integral P dV, the P is smaller. So we have more positive work, right? And less negative work. So when you go clockwise, be careful, don't use right hand thumb rule. Huh? It is not valid. So if you go clockwise, the work done is positive. Vice versa, if you go anti-clockwise, work done is negative because you're decreasing volume at high pressure and increasing volume at low pressure. Yeah, the work is positive. Is this making sense, everyone? Check it out. So when you go from A to B, so that is the thing. The all, whether it is positive or negative, the entire sign convention literally depends on that arrow ka sign. Are you going from clockwise or anti-clockwise? Any doubts on this page? Please ask me. Clear? Let's see some questions. There. So till now, whatever I did, the first was dq, which is msdt, right? This thing is straightforward. F by 2 nRT. F is the degrees of freedom. I will brief that again about degrees of freedom. The work done is a major thing. So work done is integral PdV. So if you have a process like a curve or something, A to B, area under the graph, if you're going from left to right positive, right to left negative. But if it is a cyclic process, then the work done is area enclosed, and then clockwise is positive work done and anti-clockwise is negative. Clear? Let's see a question. So we have a PV graph. This is V naught, 2V naught. This is 4V naught. This is P naught. This is 2P naught. This is A, this is B, and this is C. Find work done from A to B, work done from B to C, work done from C to A, and work done in ABCA. ABCA will become a cyclic process. Get this? It's like, just to give you an idea, if I ask you from work done to A to B, what is this? This is a curve. So I'm asking you this trapezium ka area, isn't it? Area under the curve. So you just need to find that area. Get them. I'll give you a minute. You got some answers, you can type in the chat box here to the co-host. Get them fast. It is just simply finding areas. There's nothing there. Be careful with signs. You have to tell me positive, negatives. You just everything can be positive. Hmm. So if you look at A to B, we are talking about this area. This width will be V naught. This is P naught, and this is 2 P naught. It's a trapezium. So work done from A to B, and it is going left to right. It is positive. Half into the sum of the parallel sides, P naught plus 2 P naught into the base is V naught. 3 P naught V naught by 2. Similarly, when you go from B to C, here also the arrow is going from left to right. So this is also positive. This base will be 2V naught. This is 2P naught and this is P naught. So work done from B to C is also positive, half into the opposite sides you have to add into V naught. So this guy would be 3P naught V naught. In case you forgot the trapezium area, just split this into a triangle and a rectangle. Then work done from C to A, it is one rectangle. But be careful, it is going from right to left. So it is this area. Work done from A to C is negative. The base is how much? 3V naught and the height is P naught minus 3P naught V naught. Now you can add all of them, or work done in this entire cyclic process ABCA is the area of a triangle plus it's a clockwise positive half, base is 3V naught, height is 2P naught minus P naught. And if you add all these three, you'll get the same answer. See, you should get the same answer. So if you add AB, BC, CA, that is as good as finding the whole thing. Clear, everyone? So just be careful with the signs. Easy? Just area under the curve. Clear, Arush? Adi, Abhinav, clear with us? Pratik, Jainil, Parth, clear with us? Soham, Vignajit. Let's see one more. Daksha, clear, na? Next one. V naught, 3V naught, 2V naught, P naught, 3P naught, 2P naught. This is A, B, C is this, D, E, then back and back. So you're getting how it is like an 8 shape. Find work done in A, B, C, A. Find work done in A, B, C, D, E, C, A. That's a cyclic process. Complete 8. Let's get this. We'll see that as the next one. Be careful with the signs. Clockwise, anti-clockwise does matter. Hmm. Let's see. So when you find work done in A, B, C, A, you're just finding this triangle area, isn't it? How much is that? First of all, it is going anti-clockwise. So minus half base is how much? 3V naught minus 2V naught into height P naught. So this is minus P naught V naught. Similarly, so if you look at the upper triangle, this is a positive work. That's clockwise. If you look at the bottom triangle, it's a negative work. So you can treat them as two different triangles. So work done in the entire process A, B, C, D, E, C, A is 0. Make sense? The lower circle will give you negative work and the upper triangle will give positive work. Total work is 0. You can just add the triangles. Clear, everyone? So you can separate them as two cyclic processes. You can treat this as one cyclic process and one cyclic process, and you can add them. You can have multiple cyclic processes like that. Clear? Next one. Next one. Ojas, clear, na? Surya? This is a good one, right? This can be asked even at an advanced, single more than one choice. There we have a graph like this. This is A, this is B, this is V naught, 2V naught, this is P naught, this is 2P naught. This looks like a semicircle. Is asked separately. Yeah, you still have to calculate separately. This looks like semicircle. A, B, C, D, E, C, A. Same thing. You still have to separately find upper and lower and finish it off. This looks like semicircle. The gas contains N moles, and let's say it's a helium gas. So find delta U from A to B, work done from A to B, and Q from A to B. Now, just to give an idea here, when they say this looks like a circle, you will see later on questions like this. They will draw a nice circle here. This is not a circle. This is an ellipse. The reason, think about it. See, on the y-axis you have pressure, on the x-axis you have volume. The quantities are not same. For example, instead of studying volume in terms of meter cube, if you study centimeter cube, what will happen? This graph will suddenly become like this. Na? You getting what I'm saying? This is an important thing. Even though the graph looks like a circle, you need to understand something. For example, so let's say this is y, this is x. If this is meter, right? And if you see a circle, now if you decide to study, convert meters into centimeters, you'll convert here also meter into centimeter. Then what will happen to the circle? It will still be a circle, but a bigger circle, isn't it? But let's say this y is something else, like here pressure, and this is something else, like volume. If you just decide to change volume into centimeter cube, this won't be a circle. This will become like this, isn't it? The horizontal will stretch. So you can't call it a circle. A circle is a special case where x, y, and x both are similar. So this is an ellipse since x and y have different quantities. So be careful with that. In this graph, when you see a circle, don't think it's a circle. Y and X and Y have different quantities. So you need to know this information. You will learn this later on in maths. So if you have an ellipse, this distance here 2a, this is called major axis. This is 2b, it's called minor axis, the smaller one. Area of an ellipse is pi ab. There, this information you need. Now find it. Examine, they won't tell you area of an ellipse is pi ab. By then maximum you would have done already. So, but I'm showing you. So find delta UAB, work done from A to B and QAB. Yeah, delta U is the easiest one. Right, I'll give you 2 minutes. Think about it. This would be a decent question, even at an advanced level, moderate to easy one, but it's a decent one. Work done is not that easy. You messed up something there. PV plus pi by 2. Pi by 2 नहीं अंश, pi by 4 है वो, चेक करो एक बार. Let's see the work done part. See. So you want to find the work done from A to B. So what am I asking you to find? I'm asking you to find this area, na? The entire area under that curve, isn't it? So can I split this like two parts? I will split this like this. One half ellipse plus one rectangle. So I have to find this half ellipse and I have to find this rectangle. Make sense? That total area will give you the work done. What is this length here? That is V naught, which is 2A is V naught. What is this thing here? This is B, which is P naught. So what is the area? So this is area of half ellipse is half into pi AB. So A का place में we have V naught by 2. B का place में we have P naught. So this is pi by 4, P naught, V naught. What about this guy? This rectangle, this is V naught and this is P naught. So this area will be P naught, V naught. So the total area under the curve is work done from A to B. Just add them up. P naught, V naught, pi by 4 plus 1. Is this making sense, everyone? The total major axis is this, na? Which is V naught. This is half of the minor axis. Look at this area again. The top to bottom is 2B, the left to right is 2A. But you gave only half ellipse. Is that making sense, everyone? So B is P naught, 2A is V naught. You'll get pi by 4 there. Check it out. That is the work done. Next thing, how to find temperature? We know temperature is PV by NR. So temperature at A is given by P naught, V naught by N is 1, so R. Temperature at B is 2 P naught, V naught by R. So delta U AB is nothing but F by 2 NR delta T. F is 3, N is 1, R delta T is TB minus TA, which is P naught V naught by R, which is 3 P naught V naught by R by 2. There I got delta U also. Like I said, delta U is the easiest one to find. Just find the temperature at A, temperature at B, and finish it off. Remember, this is F is equal to 3 because it's a helium gas, monatomic. You got everything. So you want to find delta Q. So delta Q AB will be thermodynamics first law, delta U AB plus work done from A to B. So just add them. So when I add them up, I end up with P naught, V naught. This will be pi by 4 plus 1 plus 3 by 2 is 5 by 2. Check. You get all the steps. Any doubts on this? Please check out the steps. So the major problem comes with that finding that area only. Most people don't realize it's an ellipse. Meaning, I'll ask you a simple question. See, this was a PYQ, okay? They gave this question. They said pressure V, and they said it's a circle. It looks like a circle. This was V naught. This was 2 V naught. This was 2 P naught. This was P naught. Find the work done. This is what they asked. I made it into an half ellipse and I made it a little more complex. How to do this thing? So again, like I said, this is not a circle, this is an ellipse. This is 2A is V naught. This was 2B is P naught. It is going in anti-clockwise, so it is a minus pi AB. So this is minus P naught V naught by 4. Clear with this? Now, for people who thought this was a circle, they got confused. Like, area is pi r square. They didn't understand, should I take r as this or r as horizontal? because it's not a circle, it's an ellipse. Clear
सर
with this? हाँ देवांश.
अपने नीचे एरो तो उल्टा बता.
ठीक है ना, but 3 arrow इस side है ना, so they are stronger.
हाँ तो आंसर तो
I wrote it wrong, record. तू भी ना. I told you some weird logic to this and answer that seems I wrote that wrong. Clear? It won't be a cyclic process then. You can't have arrows like that. All are in the same direction. Clear with this? So this was a PYQ. Check this out. Let's see one more. Any doubts on this? Let's see one more. We have a process from A to B. This is V naught. This is 5V naught. This is 3P naught. This is XP naught. X ka value is not given. This is 1 mole helium gas, so monatomic. So for this process, molar heat capacity from A to B is 13 R by 6. Find X. Remember, what is molar heat capacity? NC, TQ is NC dt, that's C. So 3P naught, 26 R V naught by 3. You made a zombie out of it. Solve properly, Ray. Don't solve anything you want. You'll get a proper number there. P naught, 3 naught, anything you wrote. Question is find X, P naught, find X. Are your dimensions even matching? It is X into P naught. It's some number into pressure. You did anything there. Hmm. Get this, get this. This will be a good advanced integer question. Let's see. Right, Ansh, you got it. नहीं अभिनव, that is wrong. नहीं, दक्षा रिकरिंग वैल्यू नहीं आएगा. Let's see. So first thing, temperature at A, 3P naught, V naught, N is 1 by R. Temperature at B, this is 5x, P naught, V naught by R. So if you want to find delta U AB, that is F by 2 NR delta T, that is 3R by 2 TB minus TA, that is P naught V naught by R, 5x minus 3. This is your delta UAB. What is QAB? QAB is NCDT. N is 1, C is given 13R by 6. dt will be again same thing, TB minus TA. P naught V naught by R into 5x minus 3. So that is 13 P naught V naught by 6, 5x minus 3. What is work done from A to B? Work done from A to B is the area under this trapezium, which is half into trapezium के लिए sum of the parallel sides, which is 3P naught plus XP naught by the base is 4V naught, which is 2P naught V naught into 3 plus X. Great. Then using the thermodynamics first law, QAB must be work done AB plus delta UAB. So basically I got everything in terms of X. Right there, right that. Substitute here, so that is 13 P naught V naught by 6, 5x minus 3, 2 P naught V naught 3 plus x plus 3 P naught V naught by 2, 5x minus 3. P naught V naught will cancel everywhere. Bring that 5x minus 3 this side, so this is 13 minus x minus 3 by 2. 5x minus 3 is 2 into 3 plus x. Multiply 3 there, 13 minus 9, that is 4. 4 by 6 will be 2 by 3. 5x minus 3 is 2 into 3 plus x. 2 will cancel. 5x minus 3 is 9 plus 3x. We get 2x is equal to 12, x is equal to 6. Check. So basically, you need to find the work done from A to B, delta U from A to B, Q from A to B, and use first law of thermodynamics. Everything will come in terms of x, so x will come out from there. This is a little lengthy, but proper advanced integer question. And again, I really didn't teach you anything. I just taught you the first law. You know how to find delta U, dq is NC dt, C is given. Work done is area under the graph. Clear, everyone? So we didn't use any hi-fi, any process and anything. Clear with this, Abhinav? Clear? Arush? Clear? Parth? Clear with this? Ahana? Got this, no? Yeah. Aryan? Clear with this? Yeah. Next thing. Let's get that. Right. Let's see. Straightforward one. Look at the first one. 20 joules of work was done on the gas. Again, remember, you're talking about a heat engine. The engine is supposed to give you work. You're not supposed to give. So work done was minus 20. 40 joules of heat was released. You don't want heat to be released. You want heat to be absorbed. So minus 40. So using the first law, Q is equal to delta U plus W minus 40 delta U minus 20. So we get delta U is minus 20. Delta U is nothing but U final minus U initial. U initial was 70. Hmm. So U final minus 70. Therefore, U final is 50. So you have to be careful with the signs. Easy question, but sign convention matters. What about the B part? Try. I'll give you another minute. So when you go from IAF or IBF, delta U will remain same. Be careful. This is not a cyclic process. Look at the arrows. Hmm. So when you go from QIAF, will be work done IAF plus UIF. So QIAF is 50. This is 20. So when you go from I to F, the change in internal energy is 30. So this is independent of the process. No matter how you go from I to F, delta U is same. So now when you go from QIBF, work done IBF, this will be UIF. QIBF will be 36. Work done, and this guy is 30. So work done will be 6 calories. Clear? So whether you go from IAF or IBF, the delta U is same. That is the main idea there. So initially you'll find delta U from IAF and then get this. All clear with this? Clear with this? There. Take a break. Come back by 7 to we'll continue again from here.
Sir, won't
Hmm.
delta U be equal to Q plus W in the A part?
Why Q plus W? This is not chemistry. Paul, be careful. Q is delta U plus W. Physics made this.
Yes, sir. Yes, sir. Sorry, sir.
Sign convention is different, na? Happens a lot. Be careful.
Yes, sir. Yes.
You- Hmm. Take a break. Come back in 10 minutes. There. Let's see one more. Let's get this. So 1 mole of a gas expands with a temperature V is equal to kT square. K is some constant. Temperature of the gas changes by 60 degrees and the work done is. So this is how they can mix it and twist it. How do you go ahead with this? Right, Viknachit. Right, Niharika. Another 20, 30 seconds. Let's see. So one thing, you want work done, there's only one formula. Work done is integral PdV. But the problem here is you are telling me the temperature is changing by 60. So you want everything in terms of temperature. Fair enough. So we have our ideal gas equation. PV is equal to nRT. And V is also kT square. So this is kT square is nRT. So P is equal to nR by kT. That is 1. And V is equal to kT square. So dV will be 2 kT dt. So substitute here. So pressure is nR by kT. And dV is 2 kT dt. kT goes off. You are stuck with 2nR integral dt, which is 2nR delta t. N is 1, R, delta t is 60 degrees. So that's 120R. So the main idea comes from there that you have to convert everything into temperature, because what is given is dt is given. They didn't give you dV, they didn't give you pressure, they didn't talk anything about pressure and volume. They're only talking about temperature change. So in the formula PdV, convert P into in terms of temperature and V in terms of temperature, and there. Now, when we started the question, we don't know you'll get the answer, but that is how your thought process goes. Continue doing that. In case you didn't get it, then you'll get back and again think of something else. Don't expect like you will know the answer, that you will get the answer till then. Most of the people have this problem, they think until unless I know what is happening till the end, I won't start. Don't do that. You have an idea, go ahead. Maximum what will happen, you won't get it. You'll get back again and you'll solve. But that's how you build your confidence. Should not be scared to do mistakes. That is one good thing about science. Like when you're doing an experiment or you're doing a problem, right? These are reversible mistakes. You do a mistake, nothing happens. You can get back and get back to work. There are irreversible mistakes. You should not do them. It's like walking a road by closing your eyes. That's an irreversible, stupid mistake. Right? Bus comes and hits you, game over. You can't do it back again. Right? After 10th standard, you decided to take, medical or engineering. That's an irreversible thing. Once you choose, you can't go back. It's very difficult. So you should take advantage of this. So you can't get scared when you're solving problems. Maximum mistake hoga, hone de na. Nothing will happen. You can get back to there. Did you notice this thing? When you're solving a question, most of the times, I have seen this. I give you a question, you're trying to solve, you have a doubt. What am I doing? Is it right or not? You keep asking, I'm doing like this. Do you think this is right? So you're waiting for someone to tell you, boss, what you're doing is right. Trust me on this. In life, you will never know what you're doing is right or wrong. Right? So don't worry about that. Go ahead. There is nothing right and wrong. There are only decisions and consequences. Luckily, in physics, these are reversible mistakes. You can always get back. Great. So that is a bit about this. Now a gas can go from A to B in infinite processes. You can take infinite paths. So we will study some 6 special cases. A gas can undergo infinite processes. We will study 6 special cases. The first one is isochoric. Now, isochoric meaning constant volume. So tell me one thing. What is more appropriate, delta V is 0 or dV is 0? This is a CT question. Which of the following is isochoric process? Options: delta V 0, dV 0, delta P 0, delta dt dP 0. They look same. They're not. When you say delta V 0, you know what you're saying? You're saying V final and V initial is same. That means, a process can look like this. You're going from here, your volume is increasing, then your volume is decreasing. Your final volume is same. So here delta V is 0, but dV is not 0. Volume is not constant. Think of like this. If you're sitting in your table, you got up, you moved around the house, then you came back and sat on the same chair. Does it mean you didn't move? You moved, right? Your final displacement was 0. This is not isochoric, right? So isochoric would look like this. The volume should not change at any point. A and B. This is how an isochoric looks. dV is 0. This automatically implies delta V is 0. You're getting it? So dV is more powerful. So when you say constant volume, remember dV is 0, not delta V. Delta V automatically becomes 0. This is not isochoric. Simple thing, but you do get confused sometimes. So how do you get this kind of process? Pretty simple. Take a vessel, take a closed vessel. Don't let it expand. So we have a heater. Put it in an insulated vessel. So the heater gives out heat. And in this process, let the temperature rise by dt. Now, the game is simple. We always want to find dq, du, and dw in all the process. That is the whole thing. So first thing, the work done. That is the whole game. We need to find these 3 in each one. Integral p dv. But dv is 0. Work done is 0. There is no expansion. Delta u. Delta u is f by 2 nr dt. This is the best thing. This thing doesn't care which process it is f by 2 nr dt. dq. This comes from calorimetry, ncv dt. So we'll call this ncv dt. So it is nc dt technically, but we will call it cv because it's a special process. So c subscript v, it means it's a molar heat capacity at constant volume. Because we are defining some special process, we felt like, instead of just calling it plain c, let's put some subscript. This is a molar heat capacity at constant volume. Now from thermodynamics first law, remember in physics is dq is du plus dw. Heat supplied is change in internal energy plus work done by the machine. So dq is ncv dt. du is f by 2 nr dt. Work done is 0. So from here we get cv is fr by 2. There we proved actually CV ka value is FR by 2, where F is the degrees of freedom. And if you see, interestingly, it's a constant one. There. But this is how you find for each process. We'll do the same thing for isobaric, thermal, adiabatic, and so on. Have a look at this page, what we did. So you need to find work done, you need to find delta U, you need to find dq, and you need to find the heat capacity. You need to find these 4 for each process. So in isochoric work is 0, delta U is this, dq is this. In the end, we'll make a table. But have a look at this page. Clear with this, everyone? Next one. Next one. CV same as molar heat capacity. Molar heat capacity for constant volume. So that V there at the tail, it simply meant we derived that in constant volume process. Isobaric, constant pressure. Again, same story, delta P0, dP0, dP0. So if dP is 0, delta P automatically becomes 0. How do you create this kind of process? We create this process by having a smooth, massless, movable piston. You keep a heater. This is a smooth, massless piston. So what is the catch with that? The advantage of a massless piston is if you take a piston, let's say the outside of the gas is P naught into area, inside is P gas into area, and let this piston accelerate with A, then we get P gas into area minus P naught into area is mass of the piston into acceleration, but this term is 0 because it is massless. Therefore, P gas is equal to P naught. Means no matter what you do, the pressure inside will remain constant. So if this gives out heat Q, so the piston will start going outside. See, if you increase the temperature, pressure will rise. If the pressure will rise, it will push the piston out. If the piston goes out, volume will increase, pressure will decrease. You're getting it? So pressure is always stabilized. So if the pressure is P naught here, the pressure will be P naught here. So you maintain a constant pressure inside. No matter how much heat you give, the pressure doesn't change. This is how you can create an isobaric process. There are multiple ways to create. This is an example. Again, same story. We want to find work done, delta U and delta Q. So work done, integral P dV. Remember, P is constant, so it comes out of the integral dV. This is V initial to V final. This would be P into V final minus V initial. Therefore, work done in isobaric process can be written as P into delta V. Or work done can be also written as NR delta T. How do we get that? We know PV is equal to nRT. Differentiate both sides. Then it will become PdV plus VdP. Product rule is nR dt. But since it is an isobaric process, this term is 0. So we get PdV is nR dt, which is work done. So both are right. You can use P delta V or you can use nR delta T. So if I know the change in temperature, I can find work done. If I know pressure and volume, I can find work done. Both the formulas are right. The second one, delta U. Like I said, this is the best one. What is delta U? F by 2 nR dt. Meaning I don't care what process it is. I'll always write F by 2 nR dt. It's a state function. But there is something here. Just now we proved in the previous isochoric that FR by 2 is CV. Are you getting it? So I can use this thing as NCV dt. Now, don't get confused. Some people will, get a confusion there. Sir, you said this is isobaric. Why are you using CV here? Clear? But now, tell me one thing. Did I say dq is NCV dt? Did I say dq is NCV dt? That would have been wrong, isn't it? I didn't say dq is NCV dt. I'm saying delta U. Now see, forget about this. Delta U is F by 2 nR dt, isn't it? And we proved in the isochoric process that FR by 2 is CV. I hope you're getting the difference. dq is not ncv dt. du is ncv dt. And because du is a state function, right? No matter which process you take, delta u will remain same. But in case that is confusing you, forget about this. Always write delta u is f by 2 nr dt. That will take care of it. I'll show you how to write dq. We didn't write dq still. So don't get confused. Don't say, why are you writing ncv dt for isobaric? This is for delta u. If I write delta q is ncv dt, then it is wrong. For delta u, you can write ncv dt because you proved that fr by 2 is cv, which is a constant. Is that argument making sense, everyone? So u is a state function. So therefore, you can write du is f by 2 nr dt or ncv dt for any process. That is the best part. You give me any process, I can write ncv dt. It's a state function, it works out. Clear, everyone? Have a look at this page. Clear? Now, what is dq? Again, from calorimetry, dq is NCDT. Again, because it is a special process, I'll call it NCPDT. There. This is what I was saying. I'm not writing CV here. What is CP? Same thing, molar heat capacity only. Technically speaking, there is no difference. It is the same C only. Just because it is a special process, we're putting a tag CP karke. Molar heat capacity at constant pressure. It's like in your school, you have your class ka leader, na? He is also student only. बस monitor करके एक tag होगा extra. There's no difference as such. Got it? Now, thermodynamics first law, dq is du plus dw. So dq is ncp dt, du is ncv dt. The work done in isobaric process is nr dt. So from here we get cp is equal to cv plus r. This is the relation between them. So we get cp minus cv is equal to r. This is called Mayer's relation. This is your HSC ka derivation. Huh? Prove cp minus cv is equal to r. You have to do literally what I did right now, all this story. Now, few points here. So in an isobaric process, if you take dq is to du is to dw, this is ncp dt, ncv dt is equal to nr dt. They will be in the ratio of cp is to cv is to r. And remember, cp minus cv is equal to r. This is one. Second thing, this is important. They did ask once. If cp minus cv is equal to r, right? If cp and cv are measured in joule per mole per Kelvin, then cp minus cv is equal to r, which is 8.3 joule per mole Kelvin, is valid for all gases. You take helium, you take oxygen, doesn't matter. It is same for all gases. But for some reason, if cp and cv are measured in kgs or grams, see what happens. So cp minus cv will be 8.3. Let's say if you take for oxygen, cp minus cv will be 8.3 joule. What is 1 mole of oxygen? 32 grams. If you take nitrogen, then cp minus cv will be 8.3 joule. 1 mole is 28 grams. So cp minus cv will not be same. So we have to be careful in what units are you measuring. So Cp minus Cv for oxygen is not equal to Cp minus Cv for nitrogen if you take in terms of grams. In moles, they're equal. Are you getting it? So in JEE, they asked a question like this. What is the relation between Cp minus Cv for nitrogen and oxygen? Luckily, they forgot to tell it is in grams. So everyone marked this answer. So they gave you marks for this also, they gave marks for this also. Are you getting this? So if they ask you this question, Cp minus Cv is equal to R, or Cp minus Cv for oxygen and Cp minus Cv for helium is same. You need to ask, are you doing it in moles? Then yes. Are you doing in grams? Then no. So by changing that units at the denominator, things get messed up. Sure, everyone. So basically the gas constant changes if you mess up the units in the denominator. Have a look at this page. Next one. Let's see our question. Hundred joules of heat is absorbed. In an isobaric process. Find change in internal energy, find work. It's a diatomic gas. Simple question, straightforward. Get this. If you supply 100 joules of energy in an isobaric process, how much will that go into delta U and how much will go into work done? How to do? Just now we wrote the statement wrong, but see, we know delta Q is delta U plus W. So whatever heat you give must go for internal energy and work. And just now we saw delta U is to W is nothing but Cv is to R. No, this ratio. Right? So what is Cv? Cv is Fr by 2. For diatomic gas, if nothing is mentioned, always check low temperature. This is F is to 2, which is 5 is to 2. That means whatever energy you are giving will go in the parts of 5 by 7 of delta Q. That is 500 by 7 joules. Work done will be 2 by 7 of delta Q, 200 by 7 joules. Making sense, everyone? So whatever energy you give will split in the ratio of F is to 2. Easy? Any doubts on that? So this is quite a good result, but I'll show you even a more powerful result than this. That is valid only for isobaric, but we can get a result for something more. The next one is isothermal process. Constant temperature, dt is 0. How do we create this? We take a vessel. We take a movable conducting piston. So if you make a conducting piston, what will happen? If the temperature inside is more, then the heat will flow out. If the temperature is less, heat will flow in. It will always maintain the temperature. So whatever energy you are giving, that will increase the pressure. So by making one side conducting, you're making it what do you call that? Constant temperature. So first thing, if constant temperature, then du is 0. Why? Since dt is 0. I mean, it's f by 2 nr dt. If dt is 0, du is 0. So there's no change in internal energy. Work done, integral pdv. But we also know from the ideal gas equation, PV is equal to nRT. So P is equal to nRT by V. So this is nRT by dV by V. V initial to V final. Work done will be nRT ln V final by V initial. Be careful, this can be also written as 2.303 log V final by V initial. It's more of a mathematical thing. If you say log, means it is base 10. If you say ln, it is base E. This is a conversion factor. If you have ln A to the base E is 2.303 log A to the base 10. Then what is dq? So dq is du plus dw, but du is 0. So dq is same as work done. Now this is an important one. What about the molar heat capacity for isothermal process? This would be a mains level question. Straightforward bits of mains level question. What is C isothermal? Again, go back to the definition. 1 by n dq by dt. The amount of heat required to change the temperature per unit degree. Can you change the temperature? No. So dt is 0. Since dt is 0, this value will tend to infinity. So C for an isothermal process is infinity. Check it out. What happened to nRT? I ate them actually by accident. Be careful, T is in Kelvin. Temperature must be in Kelvin, always. Yeah, it is dependent nRT, it is there, I forgot. Clear with this? That is the isothermal process. The next one is the adiabatic. This is the, out of all, this is the important one. The derivation is also important because if they do mess up something, you should know how to derive. So listen carefully. If you got this adiabatic, that is the deadliest one out of all four. Meaning there have been sometimes questions where the work done in adiabatic process, that's it, that formula itself was a mains level question. So in adiabatic process, they have only one thing, dq is 0. That's it. There's no other information. So net heat is 0. So heat never enters or leaves the system. You can create this process by having a completely closed vessel. Don't put any heater inside. So the heater doesn't give any heat or something. So dq is 0. So first thing from thermodynamics first law, we know dq is du plus dw. This is always valid. And ideal gas equation PV is equal to nRT. This is also always valid. Remember, these two equations will always be there. Now on top of this, you got an additional equation, dq is 0. Are you getting it? So total we got 3 equations. PV's nRT is always valid. dq is du plus dw is always valid. So dq, he gave you extra here that it is 0. Fair enough. So dq is 0. du is ncv dt. work done is PdV. Now from here, if I differentiate this is PdV plus VdP is equal to nR dt. So from here we can get n dt is PdV plus VdP by R. So bring this thing here. We have PdV minus n CV dt. Substitute that dt here, you will end up with PdV minus CV PdV plus VdP by R. Send all PdVs to one side. You will get 1 plus CV by R minus CV VdP by R. This will be PdV CV plus R minus CV VdP, right? And we also know Cp is equal to Cv plus R. So this guy suddenly becomes PdV Cp is equal to minus Cv VdP. So this can be written as dP by dV by V minus dP by P. This is Cp by Cv. Now who will write that Cp by Cv every time? So we will call it, let Cp by Cv is equal to gamma. So this guy becomes gamma dV by V is equal to minus dP by P. Clear? Now we have to integrate this. Let me show it to you in the next page. But have a look at this, what I did. So that gamma, right, is some, like, because we didn't want to write Cp by Cv every time, we defined it as some called gamma. So it didn't just come out of nowhere, it was derived like this. So then your equation gamma dV by V minus dP by P, integrate on both sides. You will end up with gamma ln V minus ln P plus some constant. So this would be ln P plus ln V power gamma is constant. This will be ln PV power gamma is constant. There. So we get PV power gamma is constant. So we derived, you getting it? There was no relation between P and V. We had to derive this. So there, these are the main stuff. PV power gamma is constant. Now I can use the ideal gas equation, PV is equal to nRT, and substitute here. Then this also becomes TV power gamma minus 1 is constant. So just write P is equal to nRT by V, you will get that. So you can put P is equal to nRT by here, you'll get relation between T and V. P power 1 minus gamma, T power gamma is constant. All three are same. You can just eliminate P, V and all and you'll get these equations. Now let's talk about that gamma a bit. So gamma is Cp by Cv. This is called adiabatic constant. So gamma is nothing but Cv plus R by Cv, which is 1 plus R by Cv. Cv is nothing but Fr by 2. This is 1 plus 2 by F. So this is the formula I like to remember, 1 plus 2 by F. So what is gamma? 1 plus 2 by F. F is degrees of freedom. It's called gamma here, adiabatic constant. It's also called Poisson's ratio in some other chapter. So physics, we have a lack of symbols. That is also called coefficient of volume expansion. What not? Physics, you want to call it whatever you want, you can call it. check it out. So there, we derived these equations for an adiabatic process. Equations were not given. And this is how the process goes. So if someone says adiabatic, you can use any of these three. It works. Gamma ka value comes from degrees of freedom. Clear? How to find gamma average? Gamma average will be 1 plus 2 by F average. How to find F average? If two gases are mixed, you can N1 F1 plus N2 F2 by N1 plus N2. There. If you have a mixture of gases, this is how you can find gamma average. Quite an important stuff. So suppose if you have 1 mole of helium and 1 mole of oxygen, then this is how you find F average, and then you get gamma average. Clear, everyone? Now, how to find that gamma and degrees of freedom, we did discuss this in KTG. I'll just show it again. This table, I hope you remember, we did last class only. There were small corrections also. This is not wrong, but this looks confusing for us sometimes. Remember, when you say vibrational mode, when you are vibrating, think of like a spring and block. You can have kinetic energy of the block and energy in the spring. So there are 2 degrees of freedom. So if you say triatomic with n vibrational mode, so one vibrational mode has 2 vibrational degrees of freedom. We did discuss this in KTG. So this will be 2n. This will be 2n, and each degree of freedom will have half kBt. So this becomes 3 plus n, 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 and n. That was a P by Q. They said a triatomic gas has 2 vibrational modes. Find gamma. So for a triatomic, you have 3 translation, 3 rotation, and 2 vibrational modes. Matlab 4 degrees of translation for vibration. That's total 10 degrees of freedom. This also will be 2 and 2 by 2. So there. Do mug up this table. This is from NCRT, so we need to follow this. This is how you find degrees of freedom for different types of gases. Clear with this? These are the main stuff. There. So we found the relation between P and V. Now how to find the work done? Story is the same. Work done is integral PdV. So V1, V2. Now we know PV power gamma is constant. So I can write this as P1, V1 power gamma. P2, V2 power gamma is equal to K, which is some constant. So I can write pressure as K by V power gamma, substitute here. This is K dV by V power gamma, limits V1 to V2. Integrate this. You will get V power minus gamma plus 1 by minus gamma plus 1, limits go to V1 to V2. This is K by 1 minus gamma, V2 by V2 power gamma minus V1 by V1 power gamma. Multiply K inside, so you'll get 1 by 1 minus gamma. But you can clearly see here, K by V1 power gamma is P1. K by V2 power gamma is P2. Your formula becomes P2, V2 minus P1, P1. There. So you get a pretty nice formula for work done. Not really that nice, but okay. P2, V2 minus P1, V1 by 1 minus gamma. And PV can be also written as nRT. So this is nR T2 minus T1 by 1 minus gamma, which can be written as nR delta T by 1 minus gamma. There. This is the work done for adiabatic process. Like I said, this itself is a question directly in some exams. Exams like, this Manipal, Vellore, or CET, right? They'll give like this only. Which of the following is the work done for adiabatic process? P2 V2 minus P1 V1 by gamma minus 1, P2 V2 minus P1 1 by 1 minus gamma. They'll just reverse that. दो options होगा ऐसा. So you have to be careful there with the signs. And this is a derivation in HSC also. It's a 4-mark derivation. They'll ask you to find the work done in adiabatic process. Check it out. So that is W. And what is the next thing? Internal energy. That is cool. And CVDT. What is delta Q? That is 0. There we found everything. There's one important thing though. What about the molar heat capacity in adiabatic process? What is the molar heat capacity? See, for adiabatic process, again look at the formula 1 by N dq by dt. dq is 0. So this is 0. Try to understand the meaning. You can change the temperature in adiabatic process without giving any heat. Na? So in every process, we have to find 4 things. du, work done, dq, and molar heat capacity. In isochoric, it was Cv. In isobaric, it was Cp. In isothermal, it was infinity. In adiabatic, it was 0. Clear with this? You see, out of all the 4 processes, this thing had a lot of stuff. There's still more. Now the problem, how does this graph look like? Because when you draw an adiabatic process and an isothermal process, they kind of look same. That was another question in one of the PYQ. They said, which of the following is adiabatic and isothermal? Let me show you how it looks. So this is a PV graph. Because look at the equations. PV is constant for isothermal and PV per gamma is constant. They both kind of look like hyperbolas. And PV is a hyperbola. PV per gamma looks like hyperbola only. So case 1, like this. Which one is adiabatic? Which one is isothermal? The red and the green. They start from the same point. So both the cases, the gas is expanding. One is an adiabatic expansion, one is an isothermal expansion. Which one is adiabatic? Which one is isothermal? This is one is adiabatic compression, one is isothermal compression. Now, which one is adiabatic and which one is isothermal? These are expansions. Gas is expanding. These are compressions. This is the problem. They both look, meaning if I just draw only one of them, you can't tell whether this is adiabatic or isothermal. So see, this is how we do. We have to go mathematically. Now, if you take an isothermal process, so in an isothermal process, PV is constant. Differentiate on both sides. PdV plus VdP is equal to 0. So we get dP by dV is minus P by V. This is your slope. So slope depends on ratio of pressure by volume. The same thing if you do for adiabatic. PV per gamma is constant. If you differentiate this, you will get dP V power gamma plus P into gamma V power gamma minus 1 dV is 0. So we get dP by dV is minus gamma P by V. Did you see the difference? Just to give an idea, look at that. For example, let's take some numbers. For example, this number is -1 and this number is -√3 because gamma is greater than 1. So tan theta -1 is how much? 135. Tan theta √3 is how much? 120. Which is more steep? When I say steep means what? Closer to 90 degrees. Who is more vertical? Adiabatic process now. So when you draw a tangent for an adiabatic process and isothermal process at the same point, the adiabatic process ka tangent will be more vertical. It's more closer to 90 degrees. So the slope of adiabatic process is more negative. Slope of adiabatic is more steep. That is the easiest way to remember. That is closer to vertical. Now try to draw the tangents. If I draw the tangent for this red line, let's call it theta2. If I draw the tangent for this green line, let's call it theta1. You tell me which one is more steep. The green one, right? So the green is adiabatic. The red is isothermal. Sure. And interestingly, what is tan theta1? Tan theta1 is slope of adiabatic, which is minus gamma p naught by v naught by tan theta2, that is the slope of isothermal process, which is minus p naught by v naught. This will be gamma. So they can ask a question like this also. They'll give theta1, theta2, and they'll ask you find gamma. So the slope of adiabatic by slope of isothermal will give you the adiabatic constant. What about this guy? Who is more steep here? You can see here red is like this. The green is actually more flattish. So who is more steep here? The red is more steep. So the green is iso here. The red is adiabatic. Check it out. Simple mains level question. Which of the following is adiabatic and isothermal? People do goof up and come. Check this out. Clear everyone? There, that is about adiabatic process. So work done, the relation between P and V, the graphs and all that stuff. The next one, the polytropic process. So a polytropic process is something which looks like PV power x is equal to constant. So this is actually a combination of all the things we did and more. So x is some variable. Be careful, this is not an adiabatic process. It looks like that. Let's see, by giving different values of x, you can create everything. So in this process, if x is 0, what do I get? In PV power x is constant. If x is 0, what do I get? P is constant, na? So if you put x is equal to 0, I get isobaric. If you put x is equal to 1, PV is constant. I get isothermal. If I put x is equal to gamma, we get adiabatic process. You're getting what is happening? If I put x tends to infinity, we get isochoric. There. So by putting different values of x, you can get different processes. So actually that means there is some process here also, na, x is 0.5. We don't have a name for that, but there are infinite processes between them. You can even have x negative also. Then the graphs will go up. These are some artificial processes, but they do exist. Clear with this? Now, if you look at the thing, same thing again, we want to find du. Du is the same story every time, f by 2 nr dt, which is ncv dt. That doesn't matter what process I give you, f is du is always same. So for work done, interestingly, think about it. Does max care whether you call this x or gamma? For max, it is simply a variable. That means whatever work you did in this thing, adiabatic, you can use the same thing here. So work done will be P2 V2 minus P1 V1 by 1 minus X, or NR delta T by 1 minus X. Just be careful. This is not valid for X is not equal to 1. For X is equal to 1, it becomes an isothermal process. The formula becomes nRT ln V final by V initial. And then we have dq is du plus dw. So dq is nc dt. So C is some molar heat capacity. D is ncv dt. This will be nr dt by 1 minus x. Nr will cancel. We end up with C is equal to cv by r by 1 minus x. Quite an important formula. So in a polytropic process, the molar heat capacity is given by this. Cv plus r by 1 minus x. Just for example, check it out. If I put x is equal to 0, what do I get? C is equal to Cv plus R. What is that? Cp, na? So x is 0 is isobaric. If I put x is equal to 1, what do I get? R by 0, infinity. For isothermal, infinity. Making sense? If I put x is equal to infinity, what do I get? Cv plus R by infinity, 0. C is Cv, isochoric. If you put x is equal to gamma, you will get C is equal to 0. So this formula is a very general formula. This will give you everything. Isobaric, isothermal, adiabatic, all the 4 processes we did, those are included in this. And this thing has even more. And like I said, this is a much more powerful formula. So if you take dq is to du is to dw, this ratio will be C is to Cv is to R by 1 minus X. This is how the work done will divide in a polytropic process. You should copy down that, put it down. We will see one question on that. You will need that. So if you know these two results, right, you can solve a lot of questions. They'll become quite easy to solve. Clear with this? Let's see a question. Let's see a question. So helium gas undergoes a process. TV cube is equal to constant. Find molar heat capacity. That's it. They'll just ask you like this. And most people will be clueless what. Remember, polytropic process, PV per X is constant, but I give T and V. So you have to convert this into PV power form and then finish it off. Get it? Remember, your ideal gas equation is always valid. PV's nRT is always there for you. minus 3/2. CVC पूछा रहे हैं. What did you find? So we have TV cube is constant. So T is proportional to 1 by V cube. So we have PV is equal to nRT. So PV is proportional to T is again 1 by V cube. So PV power 4 is constant. So therefore X is equal to 4. So molar heat capacity is CV plus R by 1 minus X. CV is FR by 2. Helium gas is monatomic. So 3R by 2 plus R by 1 minus 4. 3R by 2 minus R by 3. That is 9 minus 2, 7R by 6. Plus. Make sense? क्या कर रहे हो विहान? What are you finding, Ray? Easy? It looks easy because you know this formula. If you don't know this is a monster. Makes sense. So you convert that into PV power, this thing, and finish it off. These are polytropic processes. All clear with this? Let's see one more, last one. PV power 1.01 is constant. PV square is constant. PV minus 1 by 3 is constant. PV 1.1 is constant. So I gave you 4 processes like this. All are iso what do you call it? Polytropic. So in all this thing, or what else? Yeah. So in which process when heat is given, temperature decreases? Normally when you give heat, temperature should rise. But you do have processes when you give heat is given, temperature decreases. This would be a good question. Right? This you can frame this into an advanced matrix matching also. In which process when heat is given, work done decreases, work done increases, and I can make a matrix matching out of it. That would be deadly, but this would be the starting one. So you need to think, if I give heat and your temperature decreases, what does it even mean? Finish off, last one for the day. Think, I'll give you a minute or two. Don't worry about solving the question. Just think about that. Heat is given, temperature decreases means what? If you got that idea, then you'll proceed from there. I need to give you that also. Diatomic gas, huh? You need that. H2. Did you figure out what is the catch? Go back to the formula. dq is nc dt. It is there only. So dq is nc dt. So if heat is supplied, this is positive. If temperature is decreasing, this is negative. This is only possible if C is negative, isn't it? So for a processes where C is negative, if the heat is given, temperature decreases. That is the catch you need to figure out. Think about it. dq is positive, dt is negative, C has to be negative for this to be positive. If temperature decreases when heat is given, that means C is negative. This implies molar heat capacity is negative. There, you need to figure out that part. If you don't figure out that, then you'll be lost. There, once you got that, that is simple. When we say dq by du is negative, yeah, same thing. du is what? F by nRT dt, right? So वही हो गया ना? Now what to do? For each process you try to figure out. For the first one, what is C? Cv by R by 1 minus X. It's a diatomic gas, so it is 5R by 2 plus R by 1 minus 0.1. Yeah, this is definitely negative. That's minus 100R. So the second guy, it is Cv 5R by 2 plus R by 1 minus 2. That is minus R by 2. This is 2R greater than 0. So this is gone. This guy is also 5R by 2 plus R by 1 minus 1 by 3, 4 by 3. This is also greater than 0. Gone. This would be 5R by 2 plus R by minus 0.1. Yeah, this is also negative. So A and D are negative. Make sense? That's it. So the main idea is that whichever process has negative capacitance, then their temperature will drop when heat is given. That was the idea in the question. Sure, everyone? This question you can extend further. You can try that as an homework. In which process the work done is positive and which work done is negative. You can try that at home. Okay. So great. So we did 5 processes. There is a free expansion that we'll see in the next class. So next class when we catch up, we will also draw a table. For each process, we'll write down the work done, du, and all those formulas. Next class will be a main one. So we'll be doing the actual processes and efficiencies and all that stuff. They're not difficult. If you remember all the results, questions will go pretty easily. Okay, we'll catch up on Thursday at 5:30 as usual. So any doubts, anything, you can stay back and ask, or else you're free to leave. The paper is online till Friday, so make sure to give it. Any doubts, anything, you can stay back, or else you're free to leave.